Now that we know what closed sets are and open sets, the next thing to do is to explore the notion of compactness. So compact sets, and for this we of course we need a definition. We're gonna see what we mean by compact sets. Again, I mean, as I like to comment a little bit on how things are done in this book and how they differ from you may see, I mean, the same material covered in more advanced courses. The notion of compactness, or the definition, the definition of compactness given here is usually a consequence of a theorem that we're gonna see in a little while, which tells us that relates the a property of coverings coverings of sets by open sets, and yeah, usually that's the definition of compactness. And when you restrict things to finite dimensional spaces such as Rn or R, so R1, R, which is the same as R, then it takes on this form, or you can give this alternative definitions. But of course, this definition here only makes sense when you have a metric space. And not only that, but a finite dimensional, I mean, and many of these things only apply when you have a finite dimensional space. So you also have not only a metric structure, but also vector space structure. So the definition 3.3.1, which is the notion of compactness, takes on this following form. So a set K in R subset of R is said to be compact if every sequence in K, so all the elements in the sequence are in K, has a subsequence that converges to a limit that is also in K. So I didn't write this using quantifiers because at some point you need to be able to extract the definition using quantifiers from given statements. For instance, in papers, people don't usually write things with quantifiers. In textbooks, yes, and it's very useful because you need to get used to thinking things in this way. So there are quantifiers in the propositions. There are propositions that let you check whether a property or it holds or not. And so here, this is very important that we have to check this property for every sequence. So if you tell me, okay, this set, there's a set K that I've been given, and so in an exam or in a question, and I know that a given sequence has a convergent subsequence, that doesn't mean that the set is compact. This has to be true for every sequence contained in K. Whenever you are given a sequence in K, you must be able to find a subsequence for that given sequence that has a limit. in K. So it converges and also has the limit lives in K. And of course, I mean the what we have in mind here are, I mean, usually when we apply the I mean compact, I mean we usually when we argue by compactness or we use compactness for an argument, typically in Calc 1 you didn't actually, you used it, but you were not given the notion of compactness. I mean, some of you have not been given the usual notion of compactness, but you use this for the properties that you can use when you have functions on compact spaces. And but the most immediate examples are closed intervals. We'll see why I mean, the closed intervals are immediately compact sets. But closed intervals are just one example of many examples of compact sets. So we'll see, for instance, the Cantor set, which we did not discuss. As I said, this is not really that important for analysis. Is also a compact set, and that will come as a corollary of something that we'll see very soon. We need to now, in order to continue, we need to introduce another notion, which is a very natural one, given all the things that, I mean, all the parts where we discuss boundedness. So definition 3.3.3 is that a set A is bounded if there exists some m greater than 0 such that the absolute value of A is less than m, and this holds for all A in the set A. And again, I want you to pay attention to the quantifiers here. So in the previous definition, you have to check things for every sequence, right? To check whether whether the given set is compact or not. Here, the condition involves the existence of an m. So it's not that for every A there's an m. You have to fix the m. You have to find an m that works for all elements A in A. So this m is greater than or equal to the absolute value of every element in the set, the same m. So if you switch things around and you say that for all A in A there's an m, sure. I mean, for given any A in the set A, the absolute value of A is less than or equal to the absolute value of A. The important thing here, so that where's the information here? The information here is in the existence. So you know that there is one constant that works for all elements A in A. And now with this notion of boundedness, we have the characterization of compactness. In R. So a set K, instead of R, is compact if and only if it is at the same time closed and bounded. Okay, so there are two propositions here. So the set is compact according to the definition 3.3.1. And then if you look at that statement, that is true if and only if two things happen at the same time. The set is closed and bounded. So when you're going in one direction, so showing that the set is closed, so when you start from the hypothesis that the set is compact, so you start from this side. You want to show that the set is closed and bounded. You need to show both things. So starting from knowing that a set is compact, you need to be able to conclude that it's closed and bounded. Now, for the converse, you need to assume that the set is closed and bounded in order to be able to conclude that the set is compact. Okay, so and the proof. So I want you to think a little bit about this. So we start with one application. So compact implies closed and bounded. So we give ourselves a compact set. Let K be compact. So we need to show two things. K is bounded. K is bounded. How do we know this? So assume K is not bounded. Therefore, for every m greater than 0, there must be some x in K such that the absolute value of x is greater than m. Here we're just negating boundedness. If you will go back to the definition of boundedness, you say if there exists m greater than 0. So here there exists m greater than 0 such that for all a in A, the absolute value of A is less than or equal to m. So negating this is the same as saying for all m greater than 0, there exists A in A such that the absolute value of A is greater than m. And this is what we're using here. So we are trying to negate that. So we're saying that this set is not bounded. So okay. So then in particular, you know that this happens for every m a greater than 0. So in particular, for all, so let me write it to a more clear way. So for all n in n, there exists some x, which we're going to denote x of n because it depends on n, such that the absolute value x of n is greater than n. But according to the definition of compactness, this sequence, the sequence is well, you know that we're inside a bounded set, so the sequence contains well, I'm sorry. So we know that this sequence lies in a compact set, so we should be able to find a convergence of sequence. The sequence of the x of n's, of the x n's, does not a convergent subsequence. Because any subsequence satisfies that x of n sub k is greater than, in absolute value, than n sub k. Right, and remember, if you remember what subsequences are, this is an increasing sequence of sequence of numbers, n sub k, so the nk's go to infinity. So you have an injective function from n to n, and so an injective and increasing function from n to n, and in particular it must be going to infinity because the function takes values in n. So we know the nk goes to infinity, so the absolute value of the x nk's go to infinity. So this this arbitrary sequence here is not convergent. So any subsequence is unbounded, and that means that any subsequence is not convergent. Remember that one of the first corollaries of one of the first properties of convergence, of convergent sequences was that they were bounded. However, here any subsequence is not bounded, and therefore is not so all subsequences of this sequence are not convergent. So what have we shown? So k, we have shown k not bounded implies k is not compact. And again, this is equivalent to saying the negation of this implies the negation of that. So this is the same as saying k compact implies k is bounded. So we're done with the claim. So now, the second claim, second thing we need to show is that k is closed. Yeah, so the second claims that k is closed. And for that, we need to show that k contains all its limit points. Right, that's the definition of closed sets that we gave here. I mean, although we have, I mean, we could also prove this by using the usual notion of closeness that I mentioned before. Namely the property that, oh, that the fact that it's the complement of an open set. But here, so let's assume K is closed, and according to the definition given in the book, and let's say, I mean, we need to show that K contains all of its limit points. Limit points are points for which there is a sequence in K converging to it, right? So let X be a limit point of K. Then there is a sequence X of n such that X of n converges to X as X goes to infinity. This is one of the properties that we covered in the last video. And now we have a sequence converting to X, a sequence X of n, all containing the set K, right? So that's very important. It's in K. We know, remember we're assuming K is compact. We know there exists a subsequence sequence X of nk microversion subsequence that converges to a limit let's call it L. No, let's call the limit A, or no, B. Limit Y. Yeah, how do we know that? Because the set is compact. You have a sequence that is contained within K, it's containing K, and then you know that there's a subsequence X of nk that converges to a limit Y that is also in K. Right, that's a property of, I mean, that's the that's the definition of compactness. So remember, not only we assume that the subsequence converges to a limit, but that limit is in K, has to be in K. If we drop the requirement that the limit lives in K, then we have something that is called pre-compact. But we need not worry about such things right now. So we deal with compact sets, true compact sets. So we have a subsequence that converges to a limit Y and K. But what do we know? I mean, from before, we know that if a sequence is convergent, then every subsequence converges also to the same limit. Right? So we also know that X of nk must converge to Y as K goes to infinity. Remember, this is a property we covered as a few weeks ago. So if a sequence is convergent, then any subsequence converges to the same limit. This is not y. Converges to x, right? This implies, but then x and k is converging to y and to x. Remember that limits are unique. This is also another property we saw a few weeks ago. This implies x is equal to y, but y is in k. Which concludes the proof of the claim that the set K is closed, because we picked an arbitrary limit point, and we showed that that point, the limit point, it belongs to the set. Right, x here is equal to y, which we know belongs to K. So that concludes the proof that the set K is closed also if K is compact. Now for the converse, this is left as an exercise. Feel free to ask me about it. Should you not have time or may not have an idea on how to proceed, but the exercise in the book outlines a proof, basically more or less, and so that should be enough to get you started. And then, of course, if you get stuck at some point, just feel free to ask me and come to, hopefully, to office hours, because it's easier for me to explain things, and we're talking in person. Well, not in person, but Zoom version of being talking in person. There's one property here that I could include as part of the material, which is the nested compact set property. Tells you it is a nested sequence of compact sets, then the intersection is non-empty. But this is actually part of a larger discussion of compact sets that the book avoids, and so and this is actually really not that relevant. What is more important is the characterization of compactness in terms of the finite intersection property. The finite intersection property tells us that if you have a space is compact, so you can consider this set K as a space, as a topological space, and every time you have closed sets such that their intersection, the finite intersection of a collection of closed sets, a given collection of closed sets, is non-empty, then the intersection of all of them is non-empty, then that K is compact. So there's a finite intersection property. It's related to something that is the open cover, the definition of compact sets in terms of open covers, which is what comes next. So, this is not really providing us with any more insight. It's just a side comment, and the book avoids talking about these very important things. I'm just gonna leave it to you in case you want to read it, but I'm not gonna be testing you on that. However, it is important to know open covers because, as I said, that's the traditional way of defining compactness in terms of a property involving open covers. An open cover is, well, this is given in the definition 3.3.6, but again, this is not I mean, there's no reason to be, I mean, so, no, take things so seriously when it comes to this definition. It's very natural. So an open cover is a collection of open sets that cover the set A. Cover for A is a collection of open sets O lambda, such that lambda is in lambda. This collection need not be finite. Not only that, need not be countable. So you may have maybe, I mean, you may have one open set for every element in R, if you want. And so this is but the only thing that is required here is that this collection of open sets covers the set A. Right, so conjunction open sets such that, and this is the important thing, that sorry. Such that A is containing the union of these open sets. And yeah, using this definition, one can prove the following theorem, which is theorem 3.3.8, which gives the equivalence. This is the Hein-Borel theorem. So he said this is something that relates the notion of compactness that we've introduced to a property about open covers. So I'm actually gonna phrase this as the book does, but so the following are equivalent to three properties. We've shown, and I mean, one part was left as an exercise before, that two of these properties are equivalent, and just the third one is the new one, which I told you already is the usual definition of compactness in other courses. So three properties are that K is compact. The second one is that K is closed and bounded. And the third one is that every open cover for K has a finite subcover. So that's the third property is equivalent to being compact and being close and bounded in R. So that means that whenever you have a collection of open sets that cover the set A, you can find actually just lambda 1 up to some lambda n, and can be very large, but the important thing is you can find some n, such as choosing, you can choose n of, some finite number of among these elements O lambda, so these open sets, that still cover the set A, meaning that the union of O lambda I from I equals 1 to n still contain A as a subset, and that's it. So this is actually not, again, what's really important about this theorem is the characterization, the conclusion, and not the proof. So we're just gonna leave it here, and this is basically everything that we're gonna cover from chapter 3, and this is what's relevant for what we'll do then in the next chapters. Okay, so this is it for this part for this chapter, and we'll resume then and move to more interesting stuff in the next few videos.